Most velocity and acceleration problems involve horizontally moving objects, like a person walking along the street or a car driving along the street, things like that. So there's a kind of problem here involving dropped objects, dropped and falling objects, and they're a little more complex because you got to know some of the variables. There are things you need to pull out of the problem that you're not told, but you have to know them. Here's an obvious one right in the beginning. Now, when something's dropped, doesn't that imply that they were being held in a hand, for instance? Sure, it does. Before something is dropped, it's here in this person's hand, and its initial velocity is 0. So right there, if something's dropped, you know the initial velocity is 0. The next thing you should know is it's falling. And you're going to recall now when I remind you that the acceleration due to gravity is 10 meters per second squared. We have g for that, especially so often we have a special letter g, but we can also use a depending on the formula we're using. But in any case, you're never going to be told the ball's falling with an acceleration of 10 meters per second squared. But you know that, don't you? So you need to write that down, probably. Now, distance is a little easier. Often they'll say the ball falls 20 meters to the ground. Well, that's how far it traveled, isn't it? If it falls 20 meters to the ground, the d is 20. T is just straightforward. There's nothing unusual about that. So let's see what we got here in this little problem. Let's see if we can pull out not only what we're given in the problem, but also things we need to know because the thing is falling and was dropped. Emily drops a ball. Right away we know that the initial velocity is 0 meters per second. That falls to the ground. It's falling. We also then know acceleration, 10 meters per second squared. To the ground 20 meters below, that's our d, and then 2 seconds is simple enough. I put that over here because I ran out of spaces for the variables. And what is the ball's final velocity? That goes there, correct? Now, if you look at the formulas here, there's one right here that really fits the bill perfectly, doesn't it? We're looking for v sub f, that's what we've got here. We have v sub I, we do, is 0. We have acceleration, yes, it's falling at 10. And the time is 2. Now note, if you didn't write these things down because you know them, they're not in the problem, are they? You wouldn't have v sub I, and you wouldn't have a, and you probably wouldn't think to use that formula. But because you know those things and write them down, you'll know to use it, won't you? All right, from there in, we're just going to substitute into it like we always do and solve for an answer. And the final velocity turns out to be 20 meters per second. And there's only one more thing I want to say before I leave you on this, and that is that we didn't use d, did we? D is not in here. So we have extra information, and that's not uncommon. That's not going to bother you, is it? No, write everything down, but if you don't need it, don't worry about it. Okay, that's it. The trick with falling problems is you must know if it's being dropped with the initial velocity of 0, and it's falling, the acceleration is 10, and you'll never be told that in the problem. You must know and pull those things out and use them.